Very good.
Okay,
Welcome
thanks.
back.
Yeah, thanks everybody for letting me come back. This talk will be maybe closer to the general themes of the course than the last one. This is also work that I've done earlier. So these are themes that my book is based on, and they're kind of near and dear to my heart. So I'm looking forward to your reaction to it. In terms of formal disciplines, what I'm going to talk about today is based on classical recursion theory, effective descriptive set theory, and formal learning theory, all of which are pretty closely related. Topology is involved there too. Oh yeah, and the title, of course, is Foundations Without Suicide. So suicide is a major component of foundational thinking. And so in thinking about the foundation,
expand a little bit on that.
Yeah. And so in discussing the foundations of foundations, maybe we shouldn't always assume that suicide is necessary. Okay, so we're going to do a little philosophy. This is how Kevin thinks about the history of philosophy, or at least a lot of it. A priori certainty. The a priori is a major theme in the history of philosophy. Let's take a look at a classic view here. I'm trying to make my screen bigger. So like, I didn't want to do that. Things are getting too complicated. Yeah, so let me just read it here. So there are two kinds of truths, those of reasoning and those of fact. Truths of reasoning are necessary and their opposite is impossible. Truths of fact are contingent and their opposite is possible. When a truth is necessary, its reason can be found by analysis, resolving it into more simple ideas and truths until we come to those which are primary. A couple of major ideas there. Okay, so there's a fundamental distinction. This is a sort of a fundamental distinction that many in the 17th century would start their treatise with, between the a priori and a posteriori. And necessity has something to do with analysis. And analysis is understood in a very literal way in terms of analyzing concepts. All right. Do it. Yeah, that's much better. Okay, here's another. This is 18th century. David Hume. All of the objects of human reason or inquiry may be naturally divided into two kinds, to wit, relations of ideas and matters of fact. The terminology is a little different. Of the first kind are the sciences of geometry, algebra, and arithmetic. Propositions of this kind are discoverable by the mere operation of thought. Okay, so you can see there's a close analogy between what Hume is saying here and what Leibniz said. Going further, matters of fact, which are the second objects of human reason, are not ascertained in the same manner, nor is our evidence of their truth, however great, of a like nature with the foregoing. So these are epistemically sort of in a worse situation than relations of ideas. And for an example, the sun will not rise tomorrow. The sun will not rise tomorrow is no less intelligible than that it will rise. We should in vain, therefore, attempt to demonstrate its falsehood, where demonstration means prove deductively. Okay, so the underlying picture here is that we're doing Aristotelian logic, and so a proposition and subject predicate form has two concepts, say the concept of triangle, which is the subject, and three-sided is the predicate. And then the implicit model here, which you never really get people to carry out in detail, is that by using the mental power of analysis, you can find that triangle analyzes into three-sided plane figure, and so three-sided is contained in the concept of the subject. This is what Leibniz was talking about. And then it's just a matter of a finite procedure of pattern matching to check whether the proposition is necessary or not, necessary and a priori, or contingent and a posteriori. So in this case, the pattern matches, and so this is analytic and a priori. So a key hidden assumption here is that the process of analysis terminates, right? Because you can't do the finite pattern matching unless it does terminate. If there were infinitely many atoms in the concept of the subject, you might never get down to the ultimate analysis, and then the pattern matching wouldn't work. So you'd already, in Aristotelian logic, be facing a kind of undecided. So in matters of fact, you have something like this: the sun and rises. But then the situation looks quite different, right? Because here's a world in which the sun always rises, but no matter how many times you've seen it rise, it's always possible to be in a world where it stops rising the next day, right? And so here there's no finitary pattern matching you can fall back on. There's just looking at more and more experience, and the experience never determines what the answer is, so you get the problem of induction. So that's how Hume looked at it. This situation is very different from that situation, right? And that's why relations of ideas and matters of fact are very different. Okay. So here's an interesting thing. So Leibniz held the following view. I've said that the notion of an individual substance, so an individual substance is like a person. That's a concrete thing. Involves once for all everything that can ever happen to it. So Leibniz thought your entire future is part of your essence, because your essence should be what the medievals called a hexaity, which is a class that contains just you as a singleton, right? So there's no other possible element but you. And so that should determine everything you decide and everything you do in the future. Here's the interesting part about that. And that by looking into that notion, one can see in it everything that will ever be truly sayable of the substance, just as we can see in the nature of a circle all the properties that are deducible from it. So what he's saying is, if you have the concept of an individual, like a person, you, and you were able to do the complete analysis of the subject of any proposition that is true of you, you'd see that the predicate is contained in the subject, just like you do in mathematics. So he thought that if you could carry out that division, then all contingent truths would be just like mathematical truths. Okay, and now here's the interesting point. So there's the concept of Fred, and the predicate is Fred sins at time t, one of his favorite examples. Okay, what might happen? Well, if you're God, you can make a clear and distinct analysis of the concept of Fred and see once and for all everything that will ever happen to him. So for God, it's analytic that Fred sins at time t, just like in mathematics. But for us, we never get clear and distinct about the nature of Fred. So we've got to fall back on uncertain methods like best explanation or induction, right? And we face Hume's problem. Why? Because for us, the process of analyzing Fred's concept never terminates. Okay, so let's move forward here to Kant. Kant was a keen student of Leibniz. So here's Kant rethinking the distinction between the a priori and the a posteriori. He says it might at first be thought that the proposition 7 + 5 = 12 is a mere analytical judgment following from the concept of the sum of 7 and 5. Well, who's he talking about here? He's talking about Leibniz and Hume. That's exactly what they said. Remember, arithmetic was on the list of the a priori for Hume. So you might think that this is just analytic. For those guys, everything a priori is analytic. But we must go beyond these concepts, namely the inputs and the concept of addition, by calling to aid some concrete intuition, i.e., either our 5 fingers or 5 points, and we must add successively the units of the 5 given in some concrete intuition to the concept of 7. Hence, our concept is really amplified by the proposition 7 plus 5 equals 12. We can never find the sum by mere dissection of the concepts of the given. So what is he really saying here? He's saying this. So the concept of plus is just the recursive schema that defines plus in arithmetic, right? So that's a program. And the concepts of 3 and of 2 are successor of successor of successor of 0. But if you just analyze these concepts, you'll never get successor, 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 successor of 0. You have to do the computation, right? And so what he describes as the procedure, take the 5 fingers. Well, here we got 3 fingers. Yeah, he does too many fingers, right? So I did enough that we have that many fingers, right? So you take 3 fingers and 2 fingers. You start with the 3, you put the 2 here, and then you count successively. That just is the primitive recursive computation of plus. So he's doing primitive recursion here. It's a really interesting story. So he's kind of the first philosopher I know of for whom this idea of computational arithmetic was a fundamental philosophical idea and key to his whole system. And then without much thought, sadly, after putting so much thought into addition, he didn't think very hard about geometry and said, all principles of geometry are no less synthetical. That a straight line is the shortest path between 2 points is a synthetical proposition, for my concept of straight contains nothing of quantity, but only of quality. The attribute of shortness is therefore altogether additional and cannot be obtained by an analysis of the concept. Here too, intuition must come to aid us. It alone makes synthesis possible. So what he's saying is, in order to demonstrate a geometrical proposition, you have to do a construction, and the construction is going to be the analysis. It is going to be analogous to the successive procedures that are performed in primitive recursive addition. So for him, there's sort of no problem making this transition between arithmetic and geometry. And so here's an example of a synthesis. You actually have to use a straight edge and draw the line connecting 2 points in order to apply the axiom between any 2 points, there's a unique line incident to those points. Okay, so here's a worry that you might have. And actually, one mathematician wrote him a letter with this worry. You wish the whole discussion had been clearer, because it's hard to tell what Kant's response meant. But the worry is straightforward. If mathematics consists of universal generalizations of data drawn from pure intuition, then maybe mathematics is neither certain nor a priori, right? Because who knows how these constructions in space are going to turn out? We're drawing infinite lines, right? So how do you know whether 2 lines are going to meet? Okay, so in Kant's setup, a schema is a general rule in the understanding for producing intuitions from concepts. So in other words, you've got the data of a problem, and then a schema turns the data into a construction. So like you have the axioms of geometry, and then doing the construction with the straight edge and the compass would be the schema. So in a sense, the straight edge and the compass are the schemata. But it's mental. Okay, so for example, line of point and successor of n would be schemata. We would call those functions or constructions. And then proofs invoke these schemata, and postulates are true in virtue of our possession of the schemata. So what is it that the axioms of geometry are true of? They're true in virtue of these schemata. So Michael Friedman, in his commentary on Kant, says, the only way I can represent the existence of the circles assumed by Euclid's third postulate is by actually being in possession of the construction. And that automatically makes the third postulate true. So my being in possession of the ability to construct circles is what makes the third postulate true and demonstrative to me, right? So it's epistemically accessible because I possess the construction. That's the point. So for Friedman, as for Kant, this is a straightforward thing to say. This could be the ground of certainty in mathematics. And I emphasize, my emphasis here automatically makes, right? So it automatically makes it true. And what I want to say is, well, who says automatically? How do we know that a possessed operation will always halt with an output of a specified type? Right? That seems like a step that should be spelled out, both by Kant and by Friedman, but they don't. So for example, suppose we have Playfair's formulation of the parallel postulate, and that question is on the table. Is it true or false? I possess a straight edge. Okay, now I can do constructions with my straight edge. So I have a given line segment here. I can draw an intuition and then a point that's not incident to it. Now I can put my straight edge on this other point and start drawing extensions of that line, right? That's construction. So that's what my schemata allow me to do. Now, Kant is happy about that. But how do we know whether there's a unique line through the point that's not incident to the given line? Because the touching could happen arbitrarily far away. Okay, so I think right in the 18th century, if Kant had thought through the connection between the apodictic status or the demonstrative status of the axioms and their truth supervening on the availability of a construction, he would have seen that there's a gap in his argument. That's what so is it clear what I'm pointing to? There's a gap in his argument. Just because I possess a construction and the construction is something immanent in my mind, and the truth of the axiom supervenes on my possession of that construction, all of that together does not entail that I have mental access to the immediate mental access to the truth of the proposition, the postulate in this case. There's a gap. Okay, so now we're getting to the suicide part. Certainty and halting. Okay, so here's a scientist and he's presenting a conclusion to his peers. And, you know, look at them. They're not sure he believes that or whether they should believe it or anything. They're a bunch of skeptical jerks, as scientists always are. So he wants to impress them. So he gets out his revolver. And what he wants to do is to make it clear that he's never going to change this conclusion. Right? So that is quite impressive. We now know that he's never going to change his conclusion. So yeah, I can recommend it as a way of getting attention. And so verifiability, as it's understood in foundations of mathematics, is tied to suicide. So if the conclusion is true, you say yes and then commit suicide. And if the conclusion is false, you do anything but condition one. So you can say it's false and commit suicide, or you can never commit suicide. Either one counts as okay if the conclusion is false. So that's what verifiability means. Verifiability is a central epistemological concept. It's tied to halting, and halting is suicide. Okay, here's the classical problem of induction. So the problem of induction is also tied to suicide. So the demon here says, right, is presenting the data, and the proposition is always white, and the empirical scientist is standing there loaded and ready to commit suicide when he becomes sure that it's always going to be white. And of course, the demon is no fool here, so he won't present any black until the scientist halts with yes. So that's the classic inductive demon strategy. what I want to do is to point out an analogy between the problem of induction and halting and the halting problem and halting. Right? So now the question is whether a given Turing machine will halt. It appropriately has Turing index 666. And the formal scientist has his own number there. It's not such an interesting number. And then by the Kleene fixed point theorem, it's easy to set up a demonic machine who says, I won't halt until I see that sucker halt in my simulation of him looking at me. So using the fixed point theorem, you can easily implement exactly what everybody would recognize as the demonic strategy for the argument for inductive skepticism, right? And what drives both of those? The poor scientist and the poor computer both have losing strategies in this infinite game because they're required to commit suicide and the other guy has a move after they do it. See that, right? It's because the demon always gets one more move. No matter how late the scientist commits suicide, the demon has one more move to play after and he wins. So both of these are problems with suicide. Here's a classic result in recursion theory that to me is a really cool result. It's the Rice-Shapiro theorem. You'll see it in lots of texts, but you don't often see it with the right interpretation that makes it sound as astounding as it is. So here what we've got is a computable cognitive scientist looking at this other machine, right? And he's trying to do some cognitive science about this machine. And so we know there are two ways to do cognitive science. There's behaviorism, where you just look at the exterior behavior and you try to predict more behavior, right? Which is kind of out of fashion now. And there's cognitivism, where you posit some cognitive architecture like a program, and then you use that program to predict what the person will do, right? And it's widely thought that it's better to be a cognitivist nowadays. But let me up the ante. Suppose that in your dream of dreams as a cognitive scientist, God just hands you the program of the agent, right? So it's like the whole empirical question is over. You're given the program of the agent whose behavior you want to predict. So the question is, suppose there's something about his behavior I could verify from his program, formally, using all the apparatus available from contemporary set theory, right? Use it all. Zermelo-Fraenkel with choice, for example. Throw all that at the problem, and then suppose that we could formally verify from the program this kind of a property. Then you could have verified the property as a behaviorist computer who just empirically studies the input-output relations of the given index, right, without analyzing the code. So let me say it again. You could, whatever you could have verified formally from an arbitrary given program. So if God was guaranteed to give you the program of a system and you're supposed to verify something about its input and output. For example, it outputs 1 on input 0, something as simple as that. If you could have verified that formally by looking at an arbitrary program, you could also have verified it empirically by just looking at the inputs and outputs of the program as a black box. In other words, whatever you could, in general, verify from a Turing index in terms of behavior, you could have verified as a quasi-empiricist by treating the program as a black box.
But not termination.
Sorry?
Not termination, since then nothing comes out.
Well, no,
So
this works, but these are partial recursive.
So you can see a loop in a program code, which you can see while true do.
Yeah.
You can see it in the code, but you can't see it in the input-output behavior.
Yeah, but the point is you have to do it over arbitrary programs. Arbitrary programs, right? So some programs will be these easy ones, but some other ones won't be easy ones because they'll have, say, a mu operator with some complex arithmetical expression as the thing you're searching for, right? So that's why. So you're right. There will be easy cases, right? That's a disanalogy, but the easy cases run out, and then you have to fall back on what's equivalent to this behaviorism. So that's the other side, right? Yeah.
But it's clear to know, or just the behaviorist to know what the type of the input is and what the type of the output is?
Oh, this is just classical recursion theory, so it's nothing but numbers, right? So natural. We're doing all this on the natural numbers.
Machine and I put in zeros and ones, but maybe in the background the black box also takes a temperature or something like that, and I don't know that. So the output can differ on.
No, the only inputs to the box. So that would be another input. So the game, yeah.
Yeah, but if I don't know what inputs the machine is working with.
Yeah, that's right. So
I do have to know it.
Yeah, that's clever. That's not the point I want to make. So the inputs just are numbers here.
Okay.
Right. I'm not talking about the problem of finding out what the inputs are. I'm talking about the problem of determining what the input-output relations are. And I think it's sufficiently interesting even under that restriction. Okay. So all right, this is the Kleene predicate. Machine I produces Y and T steps on input X. And then what you can think of is the behaviorist is using the Kleene predicate to generate empirical data about some other kind of arithmetical relation. So you can think of this as like a scientist who's generating empirical data with the Kleene predicate. And then you can think of formal problems as general empirical theories. So for example, I is the index of a total function would be the empirical hypothesis for all x, there is a y, there is a t, such that ti x y t, right? So you could, if your data are instances and counter instances of t with particular numbers stuck in, then this is just what in philosophy of science you would think of as a general hypothesis of for all there is form. And so what I'm developing here is an analogy that in a universal formal problem, the answer is unverifiable. A computable daemon can fool a computable agent, and answers can run beyond all possible formal experience that you could collect using this Kleene predicate. And on the empirical side, universal empirical problem is unverifiable, and an empirical daemon can fool an ideal agent, and the answer runs beyond all possible empirical experience. So we have a really nice analogy here between halting and the problem of induction. Now there is an apparent disanalogy, and this actually I think is what you're, is what you're bringing up, right? I'm just putting it a little differently. In a universal formal problem, the input is given. In a universal empirical problem, the input is never fully given because it's an infinite sequence. There's always more data coming, right? The sun will always rise. You can keep checking. And so, in a way, this is the difference between the problem of induction and incompleteness, which is how uncomputability arises in mathematics. So you might say, well, incompleteness is a very different thing from the problem of induction, because the problem of induction is about certainty, and whereas incompleteness is you just can't get everything. It sounds very different. And I admit there is a difference there, but I'd like to emphasize the similarities, of course. And here's how we do it. So instead of saying the input is given and the input is never fully given, right? So this is one of my favorite pictures here. This is a candy that melts infinitely slowly, and that's a noodle that's infinitely long. And so if you want to stress the disanalogy, then these are two totally different situations. But of course, I don't want to do that. I want to say, what I want to say is the input is never fully taken. And in the other case, the input is also never fully taken. So actually, I like that picture is incomplete. So I want to improve the picture a little bit over here. I'll describe, you don't have to move that thing. I'll just say, I'm describing the picture with the stomach added. Okay. There's the stomach. I'm sort of reducing us to our essentials here. And here's the infinite noodle. And it's never completely in the stomach. And there's the melted part of the candy, and the candy's never totally in the stomach. So to me, that's analogous. Yeah, and then this is
I have another question.
Yeah, sure.
Is the behaviorist observing time, or have you abstracted from time in the sense that if there's an input, then instantaneously there is an output if the machine converges?
Yeah, this is abstracting from time.
You're abstracting
Yeah,
from time.
yeah.
Okay, then
Yeah.
my problem vanishes. Yes, if you abstract from time.
Of course, you know, the time would just, well, let me see. No, I take it back because, let's see, okay, so Rice-Shapiro theorem, it's a good question. I don't think, the interesting thing is that if you can formally do it, then you can empirically do it. But if you could formally do it, you could have been doing, you would have the step clicks from the Kleene predicate, right? It's telling you how many steps of computation there are. So it would be even better if I can verify anything behaviorally that in the simulation, the program, I know the steps for, right? That actually makes the result more interesting. Because in the theorem, the guy who's doing the empirical verifying isn't paying attention to that.
But
He's just looking
if the program is like this, read input, then while true, do.
Mm-hmm.
Then if you have access to the code, you can see that program will not terminate. If you need only one input,
Mhm.
one test input on the, let's say the number 0,
Mhm.
and you look at the behavior of the program from the outside, and then you wait and wait and wait and wait, since you have not abstracted from time,
Mhm.
and there is no output, but you don't know output may come.
Well, that's exactly right.
And isn't there then a difference between that the behaviorist can see less than the one who has access to the code?
The difference is in the precision of the quantifier. So the theorem is about the case where you have a total function that has to give you a 0 and a 1 for all indices.
Mm-hmm. Oh, that is already given on the outside.
Yes.
Yeah. No. It just it's a verifier, right? So it's supposed to be an RE
It
set.
has to be a fixed total index that will give you an answer for all partial indices.
You're right.
And the classes,
Okay.
and it has to also be extensional.
Mhm.
It has that. I don't think you mentioned that.
Yeah,
Of course, you can
that's
decide
right.
some intentional aspects of the source code, like is
But
the
that's why I
first-
said input-output
yeah, is
relations.
the first character, brace or something like that.
Yes.
But any extensional relation that you could decide by looking at the index, you could already decide by having the input as an oracle.
And that's Rice.
Yeah.
Well, I know
Rice-Shapiro.
Rice is.
Rice is
well, I know
Rice is that
if a set of indices is so to say, if it's closed under encoding the same partial recursive function,
yeah.
then it is it's never recursive itself unless it's empty or it contains
That's right.
all indices.
That's right. So
That's right. I
this
have
is
the
a-
right
yeah,
theorem in my mind.
That's right.
Yeah.
So that's Rice, and then Rice-Shapiro is Rice for RE sets rather than recursive sets, right? So it lifts that result to RE. That's why it's verifiable rather than decidable. So Rice is for decision. And it just says flat out that only trivial properties are decidable, right? This one's more interesting. It gives you a tighter relationship because it says that whatever is formally verifiable in general over all indices is also empirically verifiable over the functions themselves. So that, you know, it's tighter. Yeah, thanks. Okay. So here's some real disanalogies. I already mentioned it. You can't verify every true universal hypothesis in a universal formal problem, but in an empirical problem, you can verify no true universal hypothesis. So that's different, right? So that's what I meant by the difference between incompleteness and the problem of induction. It seems like the problem of induction is more severe. And compatibility with internal data is undefined, so we can't really talk about compatibility with the data that I've gathered through internal experience, because in Turing machine theory, there is no such thing. Whereas we can see how much of the noodle is in the mouth, right? So in the empirical side, it's well defined how much information you've got by a given stage. I wish I could do better. So, you know, maybe you guys with your type theory and everything can give me a better story there. But I want to respond here that it's a matter of emphasis. So on the one hand, you can think of formal proofs and certainty. That makes it look like the glass is half full. But you can also think of formal questions and the best possible means for answering them when comprehensive certainty is not feasible. So if you think of it that way, then the case starts to appear more analogous. And so that's what we're going to look at now. So this is inquiry without certainty on both sides. So we've looked at the suicidal foundations. Now on both sides, we're going to look at non-suicidal foundations, because I think of things as being analogous, right? So we're going to do gun control, something this country definitely needs more of. So if you can't halt with the truth, then find the truth in the best sense you can find the truth. So if you say, if you can't halt with the truth, do nothing, that's skepticism. That says you'd be better off not guessing anything because you can't be certain. But of course, if we held that view in empirical science, we'd have no science. So we're going to drop that. We're going to drop that idea. So a lot of people have said this: William James, Hans Reichenbach, Hilary Putnam, E.M. Gold, Peter Kugel. A lot of people are in this area. And so we're going to focus on questions, as I said. So a question partitions possible inputs into potential answers. And then I don't really care if they're finite inputs or noodle inputs, infinite inputs. You can do convergence without halting. So here's what convergence with halting looks like. It's that you might change your mind between yes and no sometimes, but then you commit suicide and you're stuck with it. Okay, and then we don't take you seriously until you commit suicide. But convergence in the limit is you can bounce around any number of times, and then you finally stop bouncing. And that's the answer you converge to. And you can do another thing, gradual convergence, which is you have a kind of a needle that's going up and down continuously, and if the answer is yes, it gets ever closer to 1. So for each distance from 1, it eventually stays above it. And then another concept is success. So success is the domain over which convergence is required. And otherwise, non-convergence is required. And so we can do success over binary partitions. In the case of binary questions, to verify A is to, right, in three different senses. In fact, so a verifying A means that you're required to succeed in A, and then you get different notions of verify if you say converge infallibly, converge in the limit, or converge gradually, right? So this is all parametric. You have different notions of convergence, different notions of success. And so on binary questions, we can use those to define what verify, refute, and decide mean. So there's decidability with certainty, decidability in the limit, gradual decidability, verifiability in the limit, verifiable gradually, etc. Okay? And then we can extend this to countable partitions. So in the formal case, right, this domain over which you must succeed turns out to be the domain of a partial recursive function, and the answers turn out to be values. So computing partial functions is a special case of problems. And in the empirical case, this is like theory choice with an empirical presupposition. Right, we have some background presupposition.
Pin code.
Shut up. This thing is useless. I said okay, that was the trouble. Go away. It's never done anything useful. Here, I'll just, sound is off. Sorry about that. Okay. And then a retraction occurs whenever one of your earlier answers is taken back. So this is the embarrassing thing. You had to reverse your opinion, right? So you wouldn't like to do that. If you shoot yourself, what suicide does is to prevent you from retracting, right? So retractions and halting are very closely connected. So we can define a kind of efficiency. Retraction efficiency equals success in the limit under the least feasible retraction bound in each answer, for example. And then we can define verifiability and refutability in the limit. I'm sorry, verifiability and refutability not in the limit, but with certainty in terms of retraction efficiency, because we can say verifiability is convergence in the limit with one retraction starting with no. And then refutability is decidability in the limit with one retraction starting with yes. So we can define verifiability and refutability in terms of retraction bounds. Okay, so here's an empirical problem. This goes back to Kant. So this is one of Kant's antinomies. So that should be apropos here. He said that, he said an interesting thing. So he's talking about what can be known metaphysically is what from experience you can somehow arrive at the right answer for, right? So he has this kind of ongoing inquiry idea. But he said, look, whether matter is infinitely divisible or only finitely divisible, whether it's atomic in structure or really a continuum, back in those days there were debates about this. Leibniz was involved in those debates, for example. And Kant said, look, this is just useless because in his German, it's outpaces all experience. This question, it's determined by all possible experience, but you never get all the experience at once. So he says the question outpaces that experience. So it's metaphysical in that sense. Well, it turns out that it does, because you can easily show using topological techniques and diagonalization that this question is not decidable in the limit. In fact, finitely divisible is not refutable in the limit, and infinitely divisible is not verifiable in the limit. And if it were decidable in the limit, then both of those would be verifiable in the limit and refutable in the limit. So it's not. Yeah, so that's what I just said. So here's how it works. I say infinitely divisible when you let me cut, right? So the axe will just bounce off if it hits an atom. It's a simple setup. So what that shows is that finitely divisible is verifiable in the limit, because if you ever stop being able to divide, then he will converge to it's not infinitely divisible, which is finitely divisible. Okay, so that gives us an upper bound on the complexity here. And then the lower bound is the daemon has a strategy. I let you cut when you say finitely divisible. And what that shows is if this guy ever converges to, if this guy ever converges to finitely divisible, then it'll actually be infinitely divisible because it'll cut forever after that. So he'll be wrong. So this is a limiting version of the skeptical argument. Here's an analogous formal problem. So is a given index an index for a total function? And then here's a way to use the Kleene recursion theorem to implement both strategies. I say total each time my current hypothesis about where he is undefined is refuted in my simulation of him. And the daemon strategy is I halt on the next input each time he says partial in my simulation of him. So they simulate each other. That generates an internal data stream for each one of them that they can respond to. And the two strategies you can see are really just the same as the strategy in the Kantian case that's empirical. Okay, so here's a historical counterfactual. I've drawn a bunch of analogies there. What if Kant had noticed this similarity, right, between total and partial computability and infinitely divisible and finite, right? So between this formal problem and the empirical problem, right? What if he had noticed what we just noticed? Well, I think it would be bad for him. But he could have done it. Right? The synthetic a priori has the problem of induction. That's what he would have concluded. And then what does that mean? He would have discovered the Gödel phenomenon in 18th century terms. He really was studying the Gödel phenomenon. Look, he came up with this, right? Here's an exact computational analog. This is like an extension of the Gödel phenomenon, because not only can you not halt with the right answer, you can't converge to it. It's exactly analogous to what Kant was doing. And yet he never thought this could happen in mathematics. It's a huge mistake. He had everything on the table to see it coming, right? Then Hilbert would not have had to study this in grammar school. Then what would his 10 questions have looked like? Okay, so here's a mixed example. So this comes from the Lucas Penrose discussion. This is about whether computers can think, right? So here's a cognitive scientist, and he's looking at a subject who might be a computer or might not be a computer. And the question is whether the behavior of that subject is computable. So you can verify computability in the limit. You just propose a program and then see if the behavior ever differs from it. It's easy. But if humans are computers, then you're a computer, in which case you can't verify in the limit that all humans are computers. That's a kind of nice, ironic result. There's something self-defeating about this. You could converge to the truth value of it, but only if it's false. So here's a picture to have. The arithmetical hierarchy is a complexity hierarchy based on how many quantifier alternations you need to define a formal predicate. And then, let's see, yeah, that's it. And so what you can do is correlate our various notions of convergent success with the complexity here, okay? So those are exact correspondences. It's easy to show that the sense in which you can converge to the truth is exactly determined by the arithmetical complexity of the formal question. And then you can stick Putnam's end-trial predicates in underneath delta 2, and that corresponds to how many retractions are required in a formal question before converging to the right answer. Okay, so these are exact correspondences. Is it clear what I'm saying here? No? Yes?
Maybe one reason people are confused, maybe that's a question. So intuitionistically, not every proposition analyzes in the arithmetical hierarchy like that. Does that have a bearing on what you're trying to tell us?
Yeah, it could. I'm not sure. So you've got predicate. So the deal is it you're defining the arithmetical hierarchy intuitionistically, or you're looking at intuitionistic propositions and they?
Yeah, then they're not. You don't have prenex normal form anymore.
Oh, I see. I see. So you just can't analyze them into that,
Yeah.
right? Right. Yeah. Of course, you don't have the De Morgan laws.
No.
Yeah. I see what I just didn't get what you were saying.
So maybe.
Yeah, all this stuff is classical, right? So I mean, all that's really going on is the De Morgan. Mainly, what's going on here is the De Morgan laws, right? And so, yeah, I don't know. Yeah, you can't use the hierarchy if you don't have De Morgan laws. I don't have any trouble with De Morgan laws anyway. The next point I want to make is that you have exactly the same picture in topology. So this is the Borel hierarchy. Instead of starting with formally verifiable predicates as sigma 1, you start with open or empirically verifiable propositions at level 1. And then you get, at the finite levels, exactly the same kind of picture. And furthermore, the finite segment of the difference hierarchy looks just like the Putnam and trial predicates. So these are the empirical analogs of the familiar computational complexity classes in classical recursion theory. And then remember the third problem about whether the student is computable or not? That's looking at empirical data, but you're looking at whether a computer could process the data and converge the truth about and converge the empirical truth. So is there a hierarchy that manages that? And yes, there is. This is the effective Borel hierarchy. So the effective Borel hierarchy, instead of starting with just open sets of infinite sequences, you start with effectively open sets of infinite sequences defined in terms of a Turing machine chomping on the sequence for some finite amount of time and then halting with the right answer, right? So you use computable functionals to define what verification means, and then everything else is the same as in the arithmetical hierarchy. So here's the whole picture. You've got an empirical hierarchy that looks like this, a formal hierarchy that looks like that, a mixed hierarchy for machine learning that looks like this. And what did Hume and Leibniz want to do? They wanted to cut the picture somewhere in the middle. Remember, relations of ideas and matters of fact. That's the first cut in philosophy for both Leibniz and Hume. Well, that would separate this one from that one, which is already strange because you're separating two things that look exactly the same. But what's even worse is there isn't a well-defined way to do it in the mixed hierarchy, because complexity can be either computational or empirical there, or a combination of both. So it doesn't even make sense. I would say the right first cut in philosophy is this one. That's the proposal. It's not that the a priori is so different from the a posteriori. It's that problems of a given complexity are different from problems of another complexity. Those are the interesting epistemological distinctions. The vertical one is not. That's my main message. Am I out of time? So that's my last message?
5 more minutes.
Okay, all right. Okay, so here's a kind of a thing that is important to me. If you're a skeptic, you say, oh, these things of higher complexity are unknowable. We'd be better off not guessing, right? And so high complexity is a reason not to believe. So negative arguments are a reason not to believe. If I do a diagonal argument and say this thing is hard, then forget it. That's halting, right? This is the suicide kind of foundation. Look at how things change if you think like a complexity theorist. So you say, look, why am I justified in using a weak procedure? It's that by a diagonal argument, I show that the problem is at least as hard as is required for that to be the best sense in which I can solve it. But solving it in the best sense is ipso facto justified. So the negative argument actually is the justification for induction. See how that works? If you require suicide, then these negative arguments in topology and recursion theory are reasons not to believe, not to do induction. But if you say what's justified is best possible performance, then the negative arguments show that induction is the best possible performance. So they're crucial to inductive justification. It just turns the skeptical argument on its head. But you have to throw away the guns. You have to disarm. Okay, here's, I'll close with this one. This is a nice result. So this is something I did with Oliver Schulte. Here's Scientific Method 101. Scientific Method 101 says, here's how science works. You have a theory, and then the theory makes predictions. So you throw a time and the theory into the theorem prover, and then it tells you what the theory predicts for the next time. Now you look at the data tape and see if that agrees. If it ever disagrees, throw out the theory. So that's how you test, right? So Philosophy of Science 101, it looks so simple. I mean, what could possibly go wrong? All this is saying, really, is that the theorem prover is insulated from the empirical data, right? Theorem proving is not empirical, so it's isolated from the empirical data. But now what if predictions are uncomputable? So there's no theorem prover to stick in there. And you are a computer. So what could possibly happen here? What's the best that we could hope for? Formal complexity doesn't always add to empirical complexity. What am I saying there? It's when you look at the overall computational problem, complexity of an empirical problem, the complexity of deriving predictions doesn't always add to the empirical complexity. They can collapse together. So that raises a question. Given that computable science can empirically determine the truth of hypothesis H in a given sense, how impossible could it be to formally derive predictions from H? Okay, so given that, say, you can converge to the truth in the limit on this hypothesis by computational means, how computable do the predictions of the theory have to be? Does everybody understand the question?
But I think that is, you put that in a box, theorem prover, whereas I think it's very often, let's say that the theory is a differential equation,
Mm-hmm.
and then you put some data in it, and then you have approximations of solutions, not exact solutions like the theorem prover will give you, and you compare the approximations of solutions to your measurements, and on the basis of that you accept or reject the theory.
Yeah, that's a friendly suggestion, right? Because when you're, if you're doing something like Newton's method, and you're not sure it's going to converge, then you are doing empirical formal reasoning, right? And so that's kind of the analogy I'm pushing. You don't think of it this way, but you could really think of it in this framework, right? In a more fundamental way. Is that these approximations don't necessarily terminate, and then they might not even be monotonic, right? The tangent may be slipping back and forth.
Not numerically stable, and so on.
Yeah, that's
even
right.
Worse than
Yeah, that's right. Exactly. So I like that suggestion. So here's a way to formalize how predictions work. And, you know, I think I'm about out of time, right? So I think I want to just cut to the chase. It turns out, so in the one paper that I listed, what we did was to solve for how complex can the predictions of a theory be, given that you can converge to the truth about the theory by computational means in a given sense. So that means, how do complexity classes in terms of learning compare to the worst complexity that deduction could be in order to be compatible with it? And the theorem works like this. You get a bifurcation. So either it can be infinitely bad, infinitely bad for the limiting cases, for these three cases, or it has to be decidable for these lower complexities. So this is not so surprising. This is what you'd expect, is that if you can verify it in the limit, decide it in the limit, or refute it with certainty, then you have to be able to derive the predictions with halting. So it's necessary that you have an isolated theorem prover. But for refutability in the limit and these others, as a matter of fact, it could fail to be arithmetically definable, so it could be infinitely complex. So that's the case where H determines a unique data sequence. It gets even more interesting when H doesn't determine a unique data sequence. Then, even for refutability with certainty, you can have infinitely complex predictions. That's kind of surprising. You can refute the thing with certainty. If it's false, you can halt and commit suicide and throw it out, even when the predictions are not arithmetically definable. So that should be interesting. Like, how the heck does that work? So this is cases, but let me just show you what the real upshot of this is, and I'll stop here. This very picture is wrong. Philosophy of Science 101 cannot realize that power. The way it works, if you look at the example that shows that you can go that high, it's that the theorem prover has to take future empirical data in order to determine whether past empirical data are compatible with the theory. You get that? There has to. So it's using future empirical data as an oracle for consistency with past data. And if so, then you can refute empirical hypotheses whose predictions are infinitely uncomputable. These are classic results, actually. This is just a little mu operation on Tarski's undefinability of truth. That's how you do it. Everybody knows that result, but it's more exciting when you think of it as saying this, right? I mean, this is classic. This is classic mathematical logic, but it's really saying this amazing thing about the limitation of science organized with a theorem prover that's insulated from future empirical data. It's a really fundamental reductio. Okay, I'll stop there.
All right, thank you. Anyone have questions for Kevin? Okay, I think we have links to your paper, so.
Okay, all right, yeah. Well,
I think.
I'd like to hear your questions. Thanks for asking them.
Okay, we'll take a 5-minute break.
All right.
Right?
Should we wait for Mark
Yeah, let's wait for Mark.
and Egbert again? It's a very wide screen, isn't it? The proportions are really
So I look at the Wikipedia and
Really what?
the statement of the Rice Shapiro theorem here doesn't involve the.
have a couple cutscenes here.
It says that I have two functions which are always in the backgrounds. And it's
I mean, that's not the aspect ratio of my laptop. I don't know why it's.
no better way to start the function. Just try.
Yeah. Yeah.
But the statement seems to be trying to compare this method with something which is not the graph.
Yeah, that's right.
So I'm really confused.
So you see, a set of indices is extensional and recursively nullable. So it's something you can verify about an index. Then it's in fact verifiable just based on.
But the input number. Okay.
Okay, so back to part 2. Now, Patrick, talk about Brouwer and the formalists.
All right. So although there was no collaboration between me and Kevin, it's nice that he gave you a little bit of background on Kant, because we will be talking a little bit about, and I do mean a little bit, but about Kant's influence on Brouwer and the formalists. I've never given a history talk before. It's mostly philosophy or math. So I found this actually quite difficult to get an interesting narrative of history out of it. Although a lot happened, it's hard to get a consistent story out of it. And I also kept something else in mind, which, I don't know, if you're like me, I prefer history talks that have interesting anecdotes and asides and give sometimes personal stories about the big players of the historical events. And it was not hard to find rather striking stories about Brouwer and Hilbert, among others. So hopefully I'll try to pepper those throughout to keep things slightly entertaining. But mostly this will be a philosophical, historical talk on Brouwer and the formalists from about 1910 to 1930, right before Gödel, when everything changed. Okay, so why this topic for this class? So we've seen a lot of different versions of constructive mathematics. We've seen a lot of guises of intuitionism, both interpretations of intuitionistic logic, as well as semantic endeavors, which we spend a lot of time on. But if you're like me, I was kind of surprised when we read Brouwer, and Brouwer said, no logic, no mathematical language, that's not part of intuitionism. I did not expect that from the founder of intuitionism to be so anti-logic when I had identified intuitionism with the logic. So what is the relationship, proper relationship between this beginning intuitionism and logic? And how did we get logic out of it? And I guess I might have been the only one who cared about this one. What were the early days of intuitionism like? Why did this come up, and why is it still around in its many different forms today? How
how did it get started and why is it still around? And although I wasn't interested at the beginning, now I am. What is the intellectual context of intuitionism? Did people care? Did people think this is interesting? Did they think it's stupid? Did they try to work through it, or did they just ignore it? Those are the kinds of questions I will hope to answer through this talk, but there are other things as well. The reason why I picked formalism as a contrast to intuitionism, to really explore what intuitionism is about, is formalism is because that's what intuitionism was, in some sense, compared to of the time. When Brouwer was around, there was no logicism, there was no really interesting philosophy of math that was not just either intuitionism or formalism, at least in Europe. And again, this is the 1910 to 1930 era. Formalism was the only comparison, really, to intuitionism. So that's why I picked this one. It's not an accident, though, that my advisor is a Hilbert scholar and such. So I will be slightly biased in talking about formalism. But we will restrict not just to intuitionism in general, but to Brouwer's intuitionism for exactly these kinds of reasons, that he wasn't a big fan of logic. He was quite adamant about lots of philosophical things. He wasn't just a logician with preferences for some rules or the others. He had really strong opinions about, well, I would say too many things, but we will restrict to his views because there are plenty to get along with. And for the formalists, we will just be talking about Hilbert and Bernays, and I'll talk about who Bernays was and why he's in parentheses. The short story is that it's almost indistinguishable between those two thinkers, which one did what. They work together so closely that they're basically one thinker. Okay, so a brief review of Brouwer's intuitionism is, well, one, it's not an entirely unambiguous term. He disagreed with himself over time. His dissertation was not, he agreed with uniformly for the rest of his career, which, as we will get to, promptly ended in 1928, through a rather dramatic and I would say petty climax that we'll get to at the end. It's very, very dramatic and entertaining. I hope you like it. But up until that time, Brouwer did not use even the term intuitionism uniformly. So we're going to have to talk a little bit about when he said what and what kinds of intuitionisms he was talking about. As a refresher, we have a couple things worth emphasizing about his intuitionism. One is the first act of intuitionism. Mathematical language is not mathematics. The more slogany version of saying this is that mathematics is independent of language. This is true in general for Brouwer. Thought is independent of language because language is a pale shadow of the things that go on in human minds. And so that's a really big tenet, and this will be one of the major differences between intuitionism and formalism. Okay, he's also quite famous, and I was kind of surprised to see that he was solipsistic and mentalistic in his conception of intuitionism. Mathematical knowledge was not proof, it was not journals, it was not publication. It was mentalistic, what happens in my brain. I can maybe represent that in some poor way with language, but the real knowledge is in my head, and it's not about communication. My job is not to communicate my knowledge to you. It's about me having my own knowledge because I'm the sole generator in some sense, the only one in charge of mathematics. But we all are our own charge of mathematics. So remember that this was a very interesting view of mathematical knowledge. Also, I want to say that I encourage you to ask questions, clarifications during the whole thing. This is kind of as a talk, but I want to treat it as a lecture. So, yes.
So I want to just emphasize the contrast of Hilbert and Bernays, where two people with one mind. Sort of
I will talk about that.
It's like anti-solipsistic.
It really is. At the very beginning, yeah, Hilbert's collaboration with Bernays is immediately anti-solipsistic. But at the same time, Brouwer published. Brouwer was very famous for his work in topology. He spent a lot of time trying to convince other people that he was right. So again, not entirely uniform treatment of his ideals through his life, even in just these 2 decades that we're treating. Yeah, certainly Hilbert and Bernays were not solipsistic, and that would be a point of contrast. And tying back in some sense to what Kevin Kelly was talking about is that there was a Kantian restriction of epistemology to intuition. Everything in mathematics for Brouwer had to be generated from some basic set of intuitions. In several papers, he explicitly calls his work neo-intuitionism. The name hasn't really kept around very long, but it was based on Kant's intuitionism. And the reason why he calls it neo-intuitionism is because he gives up one of the major intuitions of Kant. Kant said space and time are like these two basic building blocks of knowledge, especially for the synthetic a priori. But Brouwer says, yeah, space is not that important. It's about time. It's about sequence of time. It's about iteration. It's about processes.
What's the term again? Neo-intuition? What's the word?
Neo-intuition.
Oh, neo, N-E-O. So like a modified intuitionism. Although he was still very explicitly indebted to Kant for his ideas. Related to the first point, logic is not normative. It does not tell you what to do. If you ask me why I made certain inference, my answer cannot refer to logic, because logic doesn't tell us what to do. It merely records, in a rather unreliable sense, and we'll get to that, what we do happen to reason like. But logic is not a reliable representation of mathematical thought, so it cannot be a reliable way to shape our mathematical discourse. It doesn't tell us how to reason or what is justified. Okay, so that should be somewhat reviewy. A lot of these terms are rather loaded, solid segmentalistic, Kant, normative. All these things are quite robust, but we won't spend a lot of time talking about their, in some sense, the subtleties, which is why we're doing a comparison and not a close study of this. The comparison will bring out different aspects of intuitionism. Okay, so now the one that I assume you guys know less of, or at least in this class we've talked much less about, and it requires a little bit more talk. So their goal, Hilbert and Bernays' goal in creating formalism, although they never called it themselves, they were always referred to as that though, they wanted to solve foundational problems with a conception of meta-mathematics. And this comes in 3 layers. And this is a somewhat interesting, I think, interesting way of thinking about mathematics. And here's what the 3 layers in some sense say. The first layer is normal mathematics, the stuff you learn in class, analysis, algebra. Here's a definition of group, do some computations and prove these laws or something like that. Things are written in English or whatever the language you happen to speak. There's no explicit syntax, certainly not effective, and we don't have rules of inference to explicitly refer to. That's layer 1, normal mathematics, the stuff you learned before logic, if you did. Layer 2 is the formal representation of the informal mathematics. I know several people in the room do a lot of work on formalizing informal mathematics. And at this point, it seemed to Hilbert and Bernays that this was obvious and canonical way to do so. You have informal mathematics and you just formalize it. There's formulas to represent theorems, and proofs are just sequences of formulas. What's so hard about that? Of course, proof verification is not as simple as that. There's a lot of creativity and choice going on, but that's more a modern problem than a problem from this era. So that's the second layer, is the formalization of informal mathematics. The third layer is meta-mathematics. What kind of questions does meta-mathematics deal with? 1, consistency, completeness, soundness, compactness. Anything about the system itself, anything meta-theoretic. If you want to talk about semantics, for instance, you're going to be in meta-mathematics. You have normal mathematics, the formal version of such, and then meta-mathematics talks about the formal versions of mathematics. If I want to know the consistency of analysis, I can't just go to an analysis book and look for axioms. I have to formalize the analysis and then look at the consistency of the formal system. And this was, in some sense, an innovation from Hilbert and Bernays, saying, if you want to get real answers to the consistency, the completeness, etc., of mathematical theories at the turn of the 19th to the 20th century, you have to formalize first. You have to make mathematics itself, the language of mathematics, the object of mathematics. And so this 3-layer distinction for mathematics was, I would say, the central point of Hilbert and Bernays, but I don't think that's a widely accepted view. Although the 3-layer thing is accepted, I would call it central. So other people emphasize other things. things to remember is that in metamathematics, that's where consistency happens. That's what Hilbert's program gets most famous for, proving consistency. But it turns out metamathematics, this top level, the thing that talks about consistency, completeness, etc., and semantics, that level needs an a priori, intuitive, constructive epistemology. This will start a theme that I'm trying to sell in some sense, that there's a huge overlap between formalism and intuitionism. For instance, this third layer, metamathematics, is, as far as they're concerned, completely coextensional with Kroneker's finitism, and later they even claim it's exactly the same as Brouwer's intuitionism. So level 1, normal mathematics doesn't get changed at all. Nothing happens there. But once we formalize and then talk about the formalization, we have to do this intuitionistically. And this ties back to, I think, a couple weeks ago, when we talked about semantics for intuitionistic logic. One of the worries with the Kripke and Bethe semantics was that we couldn't really prove a lot of things intuitionistically in the meta theory itself. Hilbert and Bernays had exactly the right similar restriction where in the metamathematical level, we're going to do it intuitionistically. Even talking about classical mathematics, metamathematics is going to be intuitionistic metamathematics, which is what we talked about with sheaf semantics, for instance. So that, to me, was surprising when I found this out. Hilbert and Bernays were intuitionists at the mathematical level, explicitly so, saying, yep, Brouwer is exactly right for this level. Also somewhat surprising, they thought we should be skeptical of the law of excluded middle. They're like, yeah, it's not obvious. It's not super obviously valid, so we're going to have to talk about it. And I'll talk about exactly how this differs from Brouwer's view. But at first, it seems pretty close to what Brouwer would say, at least for infinite domains.
What is layer 3?
The top layer is metamathematics.
Sorry, I thought the bottom layer was.
So normal, formalized mathematics about the formal languages. So meta theory of formal languages. Which is an informal thing, right? You prove completeness informally. You prove incompleteness. Yep.
So the Hilbert Bernays conception of intuitionism, they had like a logic in mind, whereas you said like
No.
Brouwer, no.
No, neither Brouwer nor Hilbert and Bernays had a formal view of intuitionism, because that needed an a priori, intuitive, constructive epistemology. So they just had this idea of what is given to us, and it's usually the natural numbers and constructions built on the natural numbers. That's the best answer I can give you. They can mostly point to examples of what's valid in intuitionistic mathematics for them. I would say finitary, that is anything finite, totally valid. Anything based on the natural number order, including constructive ordinals, which are certainly not finite in the same sense. So it's not strict finitism like Kroneker, who said only finite numbers exist, but it's something like that. Does that answer your question?
Yeah.
Okay.
One more question. So you said Hilbert and Bernays were quite openly intuitionistic about or advocated a form of intuitionism about the metamathematical level. One of Brouwer's complaints at this point was that he never got recognized by those damn formalists.
Yeah.
So where did they say this? Afterwards?
So the problem was, I guess, when I say they were very open about this, I should say they were very clear about this. They did not publish these things. They were mostly notes for lectures. In notes for lectures, they say explicitly, formalism is taking the best from Russell's logicism. You take the fact that you can use mathematical logic, and taking intuitionism from Brouwer. They viewed formalism as the combination of logicism and intuitionism. They said, yes, mathematical logic plus restricted epistemology. Put them together, you get formalism. They say this in lectures, and they say this in notes of lectures, but these were not published, certainly not during the time. And Brouwer is correct that he didn't get credit for things, but he's also someone who over-exaggerates claims of credit, and he takes insults very, very easily.
It was for them maybe what we call the trusted core of a proof assistant.
Exactly. Yeah.
I think Brouwer would have been very happy to have seen something like that in a published manuscript from the the 20s.
Yes.
Brouwer does recognize later, and we'll get to this, that formalism and intuitionism got closer and closer as the years went on in their published forms. But he was always complaining about recognition for this closeness, he said. Hilbert takes plenty of things, or has benefited much from intuitionism, and he will benefit much in the future if only he gives credit. And I'm going to start off a little slow, but we will get to the petty tirades that both Hilbert and Brouwer gave. I think it's funny and interesting. So, but we'll do some serious stuff first. So remember that right by this time, 1910, Russell and Whitehead had written Principia Mathematica, and everyone tried working through it. It wasn't super easy by anyone who's tried. In fact, G.H. Hardy gave a hilarious, at least I think, really funny story. Is that so he was relating something that Russell told him. I can remember Bertrand Russell telling me of a horrible dream. He was on the top floor of the university library about 2100 AD. That's the year. So very much in the future, 200 years. A library assistant was going around the shelves carrying an enormous bucket, taking down books, glancing at them, restoring them to shelves, or dumping them in the bucket. So deciding what to keep and what to throw away. At last, the librarian came to 3 large volumes, which Russell could recognize as the last surviving copy of Principia Mathematica. He took down one of the volumes, turned over a few pages, seemed puzzled for a moment by the curious symbolism, closed the volume, balanced it in his hand, and hesitated. That was Russell's dream. And much later, Russell does say kind of things to the nature of, I'm not sure it was a good idea to try this. It was really hard, and he never wants to try it again. I thought that story was good. So, also by this time, Hilbert had axiomatized geometry to replace, in some sense, Euclid's geometry. Zermelo had done the same for set theory, not to replace anybody's so much as to give foundations and to avoid paradoxes, at least with hindsight. Russell had also given type theory, at least the ramified type theory with the axiom of reducibility, also in the same year, and then everyone was aware of the set theoretic paradoxes. So these are the kind of contexts that Brouwer and Hilbert are working on in 1910 to 1930. These are all accepted. And in fact, Bernays was hired by Hilbert as an assistant in 1917, in some sense to learn and teach logic with. Hilbert, surprisingly, maybe at least to me, didn't know any logic really. He had not read Frege, he had not read Principia, he had not read any of the previous Russell stuff or really spent time with it. He didn't know logic until about 1919. And so Bernays helped him do that. Although Bernays didn't know either, he just had more patience for it. Okay. Still in the historical context, I'm gonna go a little faster now. So in 1911, Brouwer coined the terms. He's actually responsible for coining the terms intuitionism and formalism for the debate. And this was in a review of Manneri's book, someone who's related to his education. He saw parts of Manneri's book to be agreeing with intuitionism and part of the book to be agreeing with formalism. And so he wanted to separate the two ideas in this one book and give them names. He placed mathematicians in each camp to give kind of ideas what he meant by the two terms. Intuitionism included Poincaré and Borel, and implicitly himself, Brouwer. In the formalist camp, and this was the very first time that this got used, so it's not really very good use of the word, but he placed Zermelo, Russell, and Hilbert. Nowadays, we do not consider either Zermelo nor Russell to be formalists. They're what we call logicists. But logicism didn't come around until Carnap, I think, coined the term maybe a decade or two later. It is funny to put Zermelo into the formalist camp, given that Zermelo was a full supporter of Brouwer's first act of intuitionism. Zermelo totally agreed that mathematical language can never represent mathematical thought adequately or completely. Seems strange from someone who axiomatized set theory, but he was actually very displeased with all the logic that Hilbert ever came out with, and he even tried to make an infinitary logic work with infinitary rules of inference, for instance, because he thought you can't reason about infinity with finite syntax. So I guess that's just a side thing. He also made a strangely strong point about the fact that until Brouwer, the intuitionists were French, and he categorized all formalists, and they were all German. This wasn't at least I didn't find this very clearly why he wanted to do this. Maybe it was, just a nice way to think about it, or maybe he was trying to make some serious political point. Either way, this reminded me of a point that, or a story that Jeremy Van Bentham, the logician, gave in a 2008 book. So Van Bentham did his PhD with the logician Martin Loeb, who was a very pure proof theorist. And as Van Bentham says, a gentleman from the grand old German school in mathematical logic and the foundations of mathematics. He goes on to tell the story. Of course, these were the revolutionary early 70s. I immediately rejected all intellectual views of my professors out of hand. He turned to modal logic, semantics, model theory, and the logician or proof theorist Loeb was disappointed. And this is where I thought this was quite funny. Himself a Jewish refugee from Germany, his view that proof theory was about deep structure, elegance, style. Qualities he attributed, not coincidentally I think, to German and Japanese cultures. Whereas model theory was about fast images, muddling through, which he associated with Anglo-Saxon and French cultures. You see where this is going? And this is all Van Bentham's story. In his highly original view of history, this explained the core alliances in the Second World War. Proof theory versus model theory. That's what the war was really about. So maybe Brouwer was talking about something related to that.
A couple of things.
Mhm.
So I think the analogy goes farther than you may have expected. I mean, there are so many great Jewish model theorists.
Mhm.
But another thing is, so I think even before, so in 1911, Brouwer is well known at this point for the fixed point theorem,
Mhm.
correct? But Emile Borel is already well known for his philosophical views.
Yeah.
So my first guess is that Brouwer would consider Borel to be a more canonical intuitionist. than Brouwer.
Absolutely. So Brouwer did not think he was inventing intuitionism. He thought he was basing his stuff on Poincaré and Borel. He thought he was continuing that tradition, although he himself was obviously not French. He did think that that was the house of intuitionism until Brouwer came along. And not until later did he consider himself the center of intuitionism. But certainly at this point, he was like, yeah, intuition is French. Look at these two guys that are very famous and very influential. Okay. So both the Hilbert-Bernays unit and Brouwer were directly influenced by Kant's intuitionism, and they both explicitly said this, both in published and unpublished works. And I will be, in some sense, playing out this overlap and the fact that in the formalist sense, they're intuitionists at the meta level, and Brouwer was intuitionist all the way through. In fact, he only had one layer, so it didn't matter. And I want to point out that Brouwer and Hilbert were quite friendly before the big debate in the 1920s. The 1920s is where the debate will happen and where the drama will start. But before then, they were extremely friendly. And here's another story, not as funny, but I think revealing. Brouwer wrote down his impressions of Hilbert after he met him in 1909. So Brouwer's just starting his career. Hilbert is in his mid-40s, already an extremely established mathematician, still already the #1 mathematician of Europe. Everyone thinks about Hilbert as the #1. So this is Brouwer's words. And again, he waxed poetic, so bear with the terminology. This summer, the mathematicus of the world, he means Hilbert, was in the Netherlands. Through my work, I was already in touch with him, but now I have over and over again walked with him and talked as a young apostle with a prophet. So he's already considering Hilbert a prophet. He was 46, but young in spirit and body, swam powerfully, and climbed with the greatest pleasure over walls and fences of barbed wire. And then he says, as if this is the only thing in his life, it was a beautiful new shaft of life through my light through my life. So I don't know why they were climbing over barbed wire fences, but apparently he did it with the greatest pleasure. So they were very friendly. They talked. They climbed over barbed wire together. I don't know how else to become friends, but that works. Okay, so we're almost done with the historical context here. As Andrew pointed out, people did view Brouwer as an excellent mathematician, especially a topologist. And I have a bunch of quotes from the major figures of the time who talk about Brouwer. So people mentioned him, and this is a little after 1911. and sometimes in recollections looking back. So Einstein recognized Brouwer's genius, but thought Brouwer, I thought this was interesting. So Einstein thought Brouwer was an involuntary advocate of the Brosius theory of the close relationship between genius and madness. So it says, yeah, Brouwer's a genius, but he's also an involuntary advocate of a theory that says geniuses are mad. Hilbert himself described in 1911 Brouwer as a scholar of extraordinary talent with a rare acumen. Very, very high praise from the mathematicus of the world, as Brouwer calls him. Max Planck noted that Brouwer was the first mathematician of the Netherlands, and together with Hilbert, the first of our time. So they were ranked right next to each other, the top of Europe. And although he always gets put second in that case, Weil himself, a student of Hilbert, although an intuitionist in some sense, said that of mathematicians I have met, Brouwer more than anybody else, with the exception of Hilbert, impressed me as a man of genius. Again, Brouwer, great. Hilbert's also pretty great. So that's what people thought about Brouwer before the debate started. And in fact, throughout the debate, his mathematical credentials were never really questioned. Like I said, Hilbert was the preeminent mathematician of the era, and he was in Göttingen, and that was the center of mathematics at the time. He made it his realm, and in some sense, he was all-powerful. Okay, so now to finally explain who this guy Bernays is, I don't know if any of you heard of him. So he joined Hilbert in 1917 as an assistant. He is well-trained in mathematics and philosophy, and I was surprised to see how well-trained he was. So to get a feel for the sort of influence Bernays had and where his training came from and how he, in some sense, fit himself into the academic world, here's his, in some sense, his pedigree. So he studied mathematics before coming to Hilbert with Landau, Frobenius, Schottky, Schur, Weil, and Felix Klein. And then he studied philosophy under Nelson, Riel, and Cassirer. And then he studied physics under Max Planck and Max Born. So that's quite a bit of education before he came to Hilbert. And of course, Hilbert was no slouch himself to teach Bernays. His students include people I think a lot of you have heard of. Gerhard Gentzen, Haskell Curry, Saunders Mac Lane. The last one is not an official dissertation advisor, but since Bernays and Hilbert were so close together, he did advise Saunders Mac Lane quite a bit, who was Steve's advisor, if you didn't know. So Bernays, although a very quiet, shy man, was basically the philosophical backbone to the Hilbert program and had quite a bit of influence. He is also the one of the co-creators for the journal Dialectica, among many other things. Okay, now we get to the philosophical agreements and disagreements. And maybe the agreements won't be surprising, but I don't think the disagreements will be that surprising. Okay. So on one axis, they could disagree on whether to be conservative or revisionary. So formalism was trying to verify mathematics in the vague sense of verify, to keep informal mathematics largely untouched, but add a mathematical apparatus, that is the second layer, the formalization, in order to study mathematics itself. So the problem, methodologically speaking, is how do we talk about mathematics correctly? Well, use mathematics to talk about mathematics. If you found a contradiction in the study, if you found a contradiction in the study, then we have to do something. But we want to give a way to compare theories and to secure the ones we have. We do this intuitionistically, like I said. The meta-mathematics is intuitionistic mathematics, and we keep all the mathematics that's consistent. Everyone pretty much assumed that through this process, we would show that mathematics as it was practiced in 15 or so when this happens, it was consistent. Okay. Brouwer had no such compunction. He wanted to rebuild or reconstruct mathematics on new foundations, restricted epistemology for all of mathematics, not just the meta-mathematics like Hilbert and Bernays, but all of mathematics. You lose some, you gain some, you change some, all for better epistemology in some sense. However, I do want to point out he was not ultra-revolutionary in the sense that he still wanted to study topology. He just wanted to do it in a slightly different way. So he didn't want to give up on all the traditions. He just wanted to mostly rebuild, reconstruct, not construct a new mathematics or build a new mathematics, but kind of revise the standard mathematics. I think I have a good quote for this too. Maybe not. Okay, so, but they agreed on something, which I've already emphasized, I think, plenty, is that for both of them, the finite natural numbers were unproblematic parts of mathematics, and they have an a priori intuitive basis. They are, in some sense, the reliable part of mathematics that we can base other things on. Formalism only had to secure things in the meta-mathematical level, so they only had to worry about the intuitive side, the meta level. Intuitionism didn't have such a level, so it just had everything in mathematics had to be based on the a priori intuitive base. But in large part, they agreed that this was the starting point for really securing mathematical foundations. In fact, some people nowadays call formalism a type of sub-intuitionism. It's like a proper subset. It uses all of intuitionism for some of mathematics. But they had a very large disagreement as well in the relationship between logic and mathematics. As we all know, Brouwer did not like logic and thought it was a pale reflection of real mathematical thought. But Bernays and Hilbert were all on board with logic. In fact, that's what they intentionally did. They took the logic from Russell because they thought it was a great way to use mathematics to talk about mathematics. It has an instrumental use, this formal logic, in providing a way to do meta-mathematics. In some sense, they were tired of doing philosophy. They wanted to do mathematics to solve mathematical problems, like methodological problems like completeness, consistency, and so on. Brouwer, of course, said mathematics is independent of language, and of course, therefore, logic. It happens in the mind, and language is inherently derivative and a poor record of mental events. And indeed, is unreliable, as we read the paper on the unreliability of the principles of logic. For the formalist side, Bernays puts it really well, I think. Mathematics no longer allowed philosophy to prescribe the method and bounds of mathematical research. Rather, it took the discussion of methodological problems into its own hands. How to do that? Well, just formalize things. That was their answer. That's how you make mathematics take its methodological problems into its own hands. You formalize. But Brouwer thought this had a really basic problem. It's a long quote, but I think the meaning is clear. It is true that from certain relations among mathematical entities, which we assume as axioms, we deduce other relations according to fixed laws, in the conviction that in this way we derive truths from truths by logical reasoning. But this non-mathematical conviction of truth or reality has no exactness whatever, and is nothing but a vague sensation of delight arising from the awareness of the efficacy of the projection onto the world of experiences and these relations and laws of reasoning. For the formalist, therefore, mathematical exactness consists merely in the method of developing the series of relations and is independent of the significance one might want to give to the relations or the entities which they relate. Basically, when you're formalizing mathematics, you're formalizing vague sensations of delight when you finish a problem. It's not a proof. There's no exact way to get this to work. You're going way beyond what mathematical proof allows. You're saying, this is the only way, this is normative, this is what we should use for proof, versus you're basing this on vague feelings of, yay, I finished the problem. Obviously, for Brouwer, that's not a very interesting line of thought to formalize vague sensations of delight. But they had an agreement, which I only hinted at before, in the law of excluded middle. Formalism and Hilbert and Bernays say that the tertium non datur is not certain in infinite domains. Asterisks, I'll get to in a second. But it is certain in finite ones. This seems perfectly fine for an intuitionist, right? I shouldn't have capitalized the D, I don't think, but it's not generally valid, is what Brouwer will say, in infinite domains. It is in finite ones. This has notions of decidability going on. The asterisk is the next step. Formalists take the uncertainty of the law of excluded middle in the infinite domains to be a problem that needs solving, not just a skepticism to maintain, but a problem to solve. How do we solve it? Show it's consistent. Done. We're not sure if the log-excluded middle is very good in infinite domains. Prove its consistency, and then it'll be good. So they're both skeptical, or at least worry about it, but then the formalist will try to solve it with some mathematical considerations, whereas Brouwer will not. Brouwer will take the basic skepticism. Yeah.
Actually, this is before like people knew a lot about incomplete, essential incompleteness and stuff like that.
Way
I
before.
think Brouwer often writes that in the same way that it is a problem to be solved. Okay, come and show me that you can decide all the statements in this theory, and then I will believe it and exclude a middle for
The
this.
very next slide will talk exactly about that. That's a good point.
Yeah.
It's the idea that the log-excluded middle is equivalent to the solvability of mathematical problems, all mathematical problems.
Yeah. That's where the real disagreement is. I mean, in some sense, I think Brouwer would be on with them that, okay, we can try to it's an uncertain principle, and we'll try to find out whether it should hold or not in some mathematical domain.
Yeah, he wasn't opposed to it, but he never really pursued it. But there's no philosophical reason, which is why this seems agreement to me. But I do want to give an interesting idea, or interesting quote from Hilbert in 1922. So he gives an interpretation of the existential quantifier that depends on the domain being finite or infinite. So the interpretation changes using the difference of notions of there is and there is available. So this is the quote. For finite totalities, there is and there is available are synonymous. So basic existentials with decidable existentials are the same. For infinite totalities, only the latter, the fact that there is available, is clear without difficulty. So he actually interprets the existential quantifier in 1922, at least in this case. At least as Becker points out, these expositions could literally have been written by an intuitionist. The interpretation of the existential seems extremely intuitionistic, as long as you don't read too much into the without difficulty part. Because Hilbert does think that you can overcome the difficulty, but it does seem that he deals with similar problems as the intuitionists do, although the solutions are very different. And yet, in this quote, and Brouwer and Hilbert are already in this debate in 1922, Hilbert doesn't give any credit to Brouwer for this interpretation. And Brouwer is, quote, somewhat displeased that Hilbert ignores his things. His things. I don't know which language or what word his things was referring to. So this is already Brouwer being kind of upset that Hilbert's not giving him recognition. Okay, now we get to the disagreement of the tertium mandatur 2. So for formalism, the log-excluded middle is not equivalent to the solvability of all mathematical problems. In fact, in the 1900 Paris lectures that Hilbert gave, he says, there is no, I always forget how to say this word, ignoramus. That is, there's no problem that's unsolvable in mathematics. And he repeats this in 1930, right before incompleteness, which is somewhat ironic. But of course, Brouwer thinks that, no, the log-excluded middle's general validity is equivalent to the solvability of all mathematical problems. This is where you get his weak counterexamples from. If you have an unsolved problem, then the general validity is not obvious, or not true.
Is that not supposed to be there in the second one?
No. Copy paste error. So they are equivalent for the intuitionist, they're not equivalent for the formalist. Thank you for pointing that out. Yes. For the intuitionist, tertium mandatur is equivalent to the solvability of all mathematical problems.
So I'm a little confused by the first one. If they are not equivalent, and according to the second sentence, using some simple, classical rules, and basically the solvability is true in some sense.
Yeah, but they didn't want to commit themselves to the truth in general of this, as this slide shows. It's not. We don't think this is generally valid, obviously, in some intuitive way, as a formalist, and so we don't want to be committed to the idea that they're solvable because we want to say there are no unsolvable questions. But if these were equivalent, then this would mean that that's generally valid. But yeah, thank you, Evan. They are equivalent for the intuitions. Okay. So this one's not that important, and I'll go quickly through this one. Consistency for Hilbert was a big deal. At the beginning, he thought if you have a consistency proof, you've proved existence. If I can prove the consistency of his geometric system, then I prove the existence of such a structure. Later, he kind of thought it was, well, just a desideratum, something you need to do for a mathematical system. He had, at the beginning, model theoretic ideas of consistency, and then once he developed proof theory with Bernoulli, he had a combinatorial, or at least syntactic version, where it's just the non-provability of falsum, or your favorite contradiction. But provability in a formal sense, whereas this is the non-formal sense. So this changed a lot, and there are entire careers based on Hilbert's program of consistency. I won't go too much into it. Brouwer didn't think much of it. He thought it was pretty irrelevant on whether a system is available to the mind. He's like, well, you've proven consistency, especially in the syntactic sense, using logic. It doesn't tell me whether I can do anything with it in my intuitionism. It doesn't guarantee legitimacy, and it certainly doesn't justify new concepts or systems. It kind of went beyond just the fact that it used logic. He also thought there was a vicious circle involved. But the vicious circle is really hard to understand. At least I don't get it. And it's worded very poorly. Okay, so now to the drama. Pennies and grudges, personal politics. Okay, so Brouwer gave a lecture in Göttingen in 1924. And Hilbert begins to strongly disapprove. Not so much of the philosophy, but basically he starts getting, if you listen to the Dutch historians on this, and they're extremely divided, like Dutch historians are extremely behind Brouwer, and then the German historians are like, yeah, Hilbert's a saint. And so depending on who you read, you'll get a very different view of how things go on. And it gets absurd of how biased they are on both sides. So most of this history is from biased sources, but hopefully they're somewhat accurate, at least when they quote things. But Hilbert starts to strongly disapprove, and he starts to get, according to the Dutch, feel threatened by Brouwer. Hilbert's status as the preeminent mathematician he starts getting threatened. So he stands up at the end of the lecture, after saying nothing during the lecture, and this is unusual for Hilbert. Hilbert always says something during the lecture. He says, with your methods, most of the results of modern mathematics would have to be abandoned. And to me, the important thing is not to get fewer results, but to get more results. And he sits down to thunderous applause. Because again, this is Göttingen, his castle. Everyone agrees with Hilbert, and Brouwer is extremely disappointed because he still idolizes Hilbert. He still is trying to get approval from this somewhat father figure to him, this prophet, this mathematicus of the world. And Hilbert denies him and does not give him the approval. In fact, one Van Dalen, a Dutch historian on this, or someone sympathetic to it, he says this. So Weil was a student of Hilbert's who, in some sense, thought Brouwer was the best. Brouwer was his favorite above Hilbert, even though he was Hilbert's student. This really made Hilbert mad, or at least frustrated. And now I quote from Van Dalen. Weil had certainly provoked his old teacher, and the mathematical world saw Hilbert's counter-offense as the proper reprimand for a person who dared to challenge the supreme commander of mathematics. Neither Brouwer nor Weil answered Hilbert's attack in kind. Both men revered the grand old man, who, by the way, was only 60, too deeply to upbraid him for a spell of impetuosity. So the world, according to Van Dalen, saw Hilbert as squashing the rebellion, these, rapscallions trying to deny Hilbert's fame and importance. I don't think Brouwer saw it this way. And in fact, another mathematician at Göttingen during this talk afterward wrote in his diary, what Hilbert expressed there seems exactly right to me. If we have to go through so much trouble as Brouwer says, then nobody will want to be a mathematician. After all, and I think it's a very ironic line, after all, it is a human activity. Until Brouwer can produce a contradiction in classical mathematics, nobody's going to listen to him. So I think it's ironic that the reason why they don't believe Brouwer is because Brouwer is not close enough to human abilities. But you can, as we've kind of seen, his set theory is not immediately intuitive. His topology is not the most natural for at least people who have been classically trained in topology. And Hilbert considers Weil's speech as often calling Brouwer the revolutionary and savior. He considers this betrayal. And so he basically, from 1924, has a mission to destroy Brouwer. At least if you listen to the people sympathetic to Brouwer. Okay, so people in Göttingen, except for that one quoted, didn't like this. Didn't like how personal things had gotten. Didn't like the tensions between Hilbert, still #1 mathematician, and Brouwer, some prominent mathematicians viewing as the #2. They didn't like this. They thought there would be much better if they collaborated, if they talked more, amicably. So they came up with a plan, straight out of a silly movie. So the solution is dinner at Emmy Noether's house, who's famous for ring theory, field theory, ideal theory, stuff like that, and focus on anything but intuitionism. This was the bright idea of Alexandrov. He saves their relationship for at least 8 months. And here's the story, which I found hilarious. So they wanted to reconcile Brouwer with Hilbert. So Emmy Noether, the one responsible for ring theory and ideal theory, among many other accomplishments, she's actually fantastic, I think. She supplied the reconciliation. Weil had asked her to host dinner with Brouwer and Hilbert, since she was, and this is a quote from Weil, warm like a loaf of bread. Already off to a great start. And then, and then now at the table, Hilbert and Brouwer, we also had Richard Courant, Edmund Landau, and young mathematicians like Alexandrov and Heinz Hopf, who co-wrote a very famous topology book together. Alexandrov started the conversation, and according to him, in his own words, the best way of getting two warring factions together is to find a common enemy. I'd give anyone points if they could figure out who it was going to be. I had no idea who it was going to be. Thus, Alexandrov brought up the subject of a famous Luckenwalder function theorist, P. Kobe. I have not heard this guy, don't know who he is. But Alexandrov's success exceeded all expectations. Hilbert and Brouwer were soon, quote, falling over themselves in a spirited exchange of opinion, during which they agreed over ever more in their view of that function theorist. The two became progressively friendlier and finished toasting each other at the end of the dinner. So they hated this function theorist, and they agreed completely about this. And by the end, and wine was definitely involved, they were very happy about each other. This lasted 8 months before the debate got even worse. I told you, this is drama. Top-notch drama here. Okay. Now, the title of this slide is going to be the title of the next, most of the slides. End of Brouwer's influence. This is how Hilbert destroyed Brouwer. This is the story. And I guess I want to, before we get into the even more drama, I want to emphasize that their philosophical differences were not that great. In fact, they lessened as time went on. And by 1928, as I'll repeat at the very end of this, Brouwer even said, except for a couple of minor things, the difference between the two was a matter of taste. It started as a real opposition, but at the end, even Brouwer was like, it's just a matter of taste now between the philosophical doctrines. But by 1924, and then after again the dinner, it wasn't really about philosophy. It wasn't even really about mathematics. It became really personal, and that's why this thing happened. And depending on who you ask, it's someone else's fault. It's Brouwer's fault for being a strong personality. It's Hilbert's fault for being, power hungry or something like that. Doesn't really matter to me. But what does matter is that this does end Brouwer's influence as a mathematician, especially as one that talks about foundations. In fact, in a visit to Princeton in the 30s, people felt really sorry for him, but didn't listen to him anyway. So Brouwer visited Princeton in the 1930s, and people felt very sorry for him, and he felt very sorry for himself, and started trying to talk up how bad he had it, but no one listened to him, his mathematics or his foundations in the 30s. And he lived to a great old age, so he was around for a long time, completely abandoned by the mathematical community. But this was not because of philosophical success or non-success. In fact, he was successful to get Hilbert to basically adopt a form of intuitionism. And yet, I think Brouwer and his sympathizers are correct that he does not get the credit he needs for creating what became the standard, which is Hilbert's program, which is why so many people, like in this department, this philosophy department, do formalization. It's because of Hilbert. And yet we don't remember that it's because of Brouwer that it works the way it does. I mean, why do we do Martin-Liff peg theory? Martin-Liff was extremely influenced by Brouwer. So although this thing will get purely personal from now on almost, it doesn't actually reflect the philosophical differences. And that's what's almost frustrating to anyone sympathetic with Brouwer, is that his ideas carried on in Hilbert's form, and yet Brouwer got completely marginalized after 1928. Here's the story of how Brouwer got marginalized. Okay, so this is after the First World War. The International Council of Research was a branch of the League of Nations, and it boycotted German, Austrian, Bulgarian, and Hungarian scientists. In fact, it even, so they couldn't go to any international conferences. You also couldn't speak German in scientific discourses. It was a full ban on German languages in scientific discourses, not German languages, German, pushing to English and so on. Brouwer, though himself safe from these issues as not being German, Bulgarian, Hungarian, Austrian, campaigned heavily against this situation. He thought that Germans and the rest should be included in international conferences. He was extremely adamant and tried to lobby the committee on the International Council of Research, or whatever it's called, to allow German participation. Funny enough, on a related committee that influenced this committee on research, Mussolini was the head of. So it was extremely political at this time. But then, I don't think it's due to Brouwer at all, but then the boycott on Germans was lifted. They could attend international conferences again, but they were not allowed, they were allowed to give lectures, but they were not allowed to be full members of the conferences. For instance, the International Congress of Mathematicians happened in 1928, when this will happen. I think I actually have points I should be showing you. And this is going to be, the International Congress is going to be held at Bologna. So the council changed their opinion and they allowed Germans to come to the Bologna conference. And this is a big deal. Some German and Austrian mathematicians did indeed join Brouwer, who started advocating the boycott of this conference. They said, don't go to the Bologna lectures, boycott this. This committee does not get to control you. If you have the bravery of Germans, don't go. And some, and he also said this to Austrians, and some did join Brouwer in avoiding the conference. There was no official delegation from Berlin, for instance. Hilbert went, didn't care what Brouwer said, and he came with a large contingent from Göttingen, of course, still extremely influential city and department. And he strongly opposed the boycott. In a draft of his own letter, where Brouwer sent out a letter advocating everyone to avoid the conference, Hilbert sent out a letter that said he viewed the boycott as political oppression. And this quote is worth stating in full. In Germany, this is Hilbert. In Germany, a political blackmail of the worst sort has come into being. You are not German, German birth unworthy, if you do not speak and act as I now prescribe you. It is very easy to get rid of this blackmail. One need not only ask them how long they have laid in the German trench. Unfortunately, German mathematicians have fallen victim to this blackmail. For instance, Bieberbach was on Brouwer's side. Brouwer has understood how to make use of the situation of the Germans, and without himself giving a hand in German trenches, causing all the more incitement and discord among the Germans, in order to pretend being the master of German mathematicians. With all success, he will not succeed a second time. So Hilbert viewed Brouwer as a political oppressor to Germans, completely appropriating German struggles, German problems as his own, saying, I am the champion of Germans, I will protect you. And Hilbert finds this to be blackmail. Of course, that means he feels insulted by Brouwer's involvement in this whole thing. He was not in the trenches. He's never been, had problems that the Germans had. Turns out, most people listened to Hilbert. Germans were only outnumbered by Italians at the Bologna conference. The only notable exception being Bieberbach, who was somewhat prominent at the time. Okay. Something I didn't say But Brouwer was on the editorial board for the Mathematische Annalen, which was the major, single most influential journal in all of the mathematical communities, especially in the West. And he put him on the editorial board in 1915. Again, Brouwer was extremely respected as a mathematician. And this was extremely good for Brouwer's career, among other things. Brouwer immediately accepted. He thought this was a great honor. And indeed it was. The chief editors were Einstein, Hilbert, Carathéodory, and Blumenthal. I think they say Carathéodory. But when Hilbert returned from Bologna, he wrote to Brouwer that he was now dismissed as a member of the editorial board. Hilbert, unilaterally, without asking any of the other editors, just wrote a letter to Brouwer dismissing Brouwer from the editorial board. Carathéodory, who was Brouwer's friend and disagreed with Hilbert's decision, got a telegram before Brouwer got the letter, and so warned Brouwer, hey, you're being dismissed. Hilbert's going to dismiss you from the editorial board. However, in the end, Carathéodory did agree with Hilbert because Hilbert got sick. Hilbert was really sick, and so Carathéodory felt pity, and so agreed with Hilbert's view that Brouwer should leave. I don't really understand why. But Hilbert was sick, so Carathéodory, in some sense, abandoned Brouwer in this sense, although he did still warn him. Einstein refused to give in to Hilbert's demands, and Hilbert wasn't king of the journal. He was just one editor, so was Einstein. And he pleaded. He said to Hilbert in a letter, "Sire, give him a jester's freedom." Not exactly the most supportive to Brouwer, calling him a jester, but at the same time denying Hilbert's power to unilaterally kick people out of the editorial board. And Brouwer told Carathéodory that he would comply with Hilbert's request only if Hilbert's physician would state in writing that Hilbert was of unsound mind. Only because the only reason why Hilbert would ask that is since he's sick and he's of unsound mind. He's an insane person. He said this in writing in the letter. Blumenthal, who I have not mentioned yet, but is the fourth major editor, main editor of the journal, found this extremely tactless and turned on Brouwer and joined Hilbert. So he was extremely offended by this request. So Brouwer's like, I will not leave unless Hilbert's deemed insane. And Blumenthal's like, whoa. All right, that's too much. So the only solution that was to be had, because Einstein and Carathéodory, in the end, did not want to kick out Brouwer. Of course, Brouwer didn't, but he didn't have a choice. And Hilbert and Blumenthal did. So it was in some sense a split vote, if it was democratic. So instead of trying to figure out how to solve this, they just dissolved the editorial board. And maybe not surprising, Hilbert, Blumenthal, and the mathematician Hecke created their own editorial board. Didn't have Einstein, didn't have Carathéodory, and of course, never had Brouwer. So Hilbert gets back from the Bologna lectures, sends a letter without talking to the other editors that Brouwer is no longer an editor of the journal that everyone wants to be an editor of. Drama ensues, and so they just dissolve the board, and they make a new one. Brouwer is devastated by this. So not only was it an honor in 1915 when he got offered this job, extremely harmful when he lost it. Let's see, what was it? I mean, he idolized Hilbert, and the fact that Hilbert turned on him so fully to kick him out of the one job he actually liked ruined him. And although there's no good record of how Brouwer responded to this exact thing, other than deep depression, which is understandable, I have a couple anecdotes on how Brouwer reacted in general to things that upset him. He was a bit of a touchy person. So in this side, basically, after negotiating more pay for his job in Amsterdam by leveraging offers from Berlin and Göttingen, which Hilbert offered him a job at Göttingen because he thought he was a great mathematician. Brouwer immediately left for Berlin after getting more pay from Amsterdam. So he went back to Berlin. Friedrich van Eeden, a good friend, wrote in his diary, a good friend of Brouwer, "I heard that Brouwer was in the country and left again for Berlin. He has wounded himself with some glass when he kicked in a window in his house because it was closed. And that without telling me. He loves me after all in another way than I love him." Okay, it's a little odd that he kicked in his window to get in his house. Van Dalen comments that, indeed, Brouwer was short-tempered where such obstructions as closed doors or the like were concerned. A classic category of anger. And Brouwer used to drop in occasionally to see a journalist living in Belgium with whom he was on good terms. So there's another case of this. Once, when he did not find the journalist in his office, Brouwer got so angry that he kicked in the window. Interesting. Fraenkel, who we all basically remember from Zermelo Fraenkel's set theory, was an extremely integral part of, had extremely integral parts into the foundational debates of this era, including his very influential book, Introduction to Set Theory. And in that introduction, he includes part of intuitionist set theory based on Brouwer's work. And he tries to represent stuff that Brouwer hopefully will agree with. He's like trying to, do this accurately. He's extremely impartial, very neutral. He's trying to represent Brouwer's intuitionistic set theory inside of his set theory book. So he sends a manuscript to Brouwer asking for comments, like, is this what you believe? And there was one comment on the Cantor-Van Dixon theorem, which states that every closed set is a disjoint sum of a countable set and a perfect set. The details obviously don't matter that much. He thought that was trivially true in intuitionistic set theory. And Brouwer has published something that said the same thing. Brouwer changed his mind and thought that that was not the case. It was trivially true for deconstructible sets, but not in general. And so his view changed as well, but Fraenkel didn't know this. But Brouwer, of course, thinks that he should have known this, obviously. And this is the quote from a letter from Brouwer to Fraenkel. "Should you stick to this insulting and hollow insinuation that he believed the Cantor-Van Dixon theorem is true, even after my urgent request and urgent advice to strike them out, then the competent reader, as I claim to be myself, can only read this as a declaration of war on me. I ask myself in vain what grounds I may have given you. Forgive me that I write sharply and clearly, but I have to do this also in public." So he was not one to let things go. He was described as a good friend, as an expert at nurturing grudges. And in some sense, it was that personality combined with Hilbert's desire to keep his power status that in some sense ended Brouwer's career. So now we're going to have a little recap.
Make it quick. Get out of time.
This is the last slide. So back to philosophical stuff. Formalism and intuitionism, as doctrines, were largely compatible. They were motivated by similar tendencies. In fact, both explicitly so by Kantian tendencies. We don't want to do this Platonic access realm stuff. We want to have a constructive, and they both use the same phrase, constructive. Hilbert more than Brouwer. Ways of constructing objects, of proving things. The locus of intuitionism for Hilbert and Bernays was the meta level. The locus for Brouwer was, of course, all of mathematics. But as they grew, as philosophies go, they got closer and closer. And as I said, in 1927, 1928, right before the journal debacle, when he got kicked out of the journal, he claimed that except for the equivalence of the tertium non-datur to the solvability of problems, it was a matter of taste. And that's pretty surprising to me. I thought these were kind of mutually exclusive philosophies of mathematics, and we get told this a lot. In fact, in our philosophy department, we read an article that gives us the tripartite distinction: logicism, formalism, intuitionism, and all three articles say, like, yeah, this is the only one that's correct. During the time, logicism wasn't a thing, and formalism and intuitionism were very, very close, which I found surprising. So I also want to say, yeah. But this closer and closer of philosophical doctrines, and by some commentators, was the explanation for why it got so personal, is that Hilbert felt more and more threatened by Brouwer's fame because he was starting to say similar things, or at least Hilbert was starting to say similar things to Brouwer. I'm not sure if I agree with that. I'm not super expert on this, but the philosophical closeness was followed almost immediately by deep and harsh falling out between protagonists. And I do want to say, except Bernays, who kept extremely cordial relationships to all of them. No one was ever angry at Bernays. And someone who's famous for making fun of people, Georg Kreisel, never said a bad word about Bernays. The one person, and I think Saul Pfefferman even says this, the one person Kreisel never disliked was Bernays, which is something to say, I guess. And it removed all hope of reconciliation. Brouwer completely left the foundational debate, and in some sense, Hilbert won. And you can kind of see that now. You can kind of see what people spend their time doing in foundational research these days. And the fact that proof theory is so prominent does say something about Hilbert's success. And the fact, again, that we think of intuitionism as a type of logic and not as a philosophy of mathematics so much, again, attests to Hilbert's success. That formalizing mathematics is the first step to getting an interesting philosophy. So as I assume, at least the people I've talked to, were also under the impression that intuitionism was intuitionistic logic. When I wrote a paper that did this, and Wilfried, my advisor, says, no, intuitionism is Brouwer, intuitionistic logic is not Brouwer. So Brouwer lost this debate. People took the formalist mathematical logic side much more in hand than any of the stuff that Brouwer did, especially for his set theory. Although not to say that constructivism isn't influential, which of course it is, but Brouwer's type, it lost. Okay, so that's the Brouwer and the formalists.
We're over time, but we can have perhaps the question if there's burning with a question.
I hope it wasn't too boring.
It was fun.
Yeah.
That's fine. So,
But
back to the first slide. the second slide.
second slide?
It's about the characteristics of the equations. So as far as I remember, the characteristics of being solipsistic, cognitive Brouwer doesn't prevent communication.
It certainly doesn't prevent it.
Communication is kind of second grade.
Exactly.
But it's possible to recreate the same whatever. It's a mental process. Mental construction.
Yes, you can do work to represent what happened in the mind of the creative agent. But Brouwer, at least in several instances, he doesn't always say this, but it's not a full representation. The true mathematics is still in the mind of the mathematician, and you can represent parts of it by communicating, by publishing things.
And then the goal is to recreate the same thing.
Yeah.
By another.
Some type of empathetic idea, yeah. I have an idea, I do my mental stuff, which is mathematics. I write something down, hoping that you do the same mental stuff.
Yeah.
Yes. But it was always a lossy procedure. And so it didn't preclude him from publishing, but in his more philosophical and mystical writings, he was very strong, and that language was a lie. he says this all over. In lots of contexts.
I mean, I just want to say that it seems that there's a way to, it's secondary, still communication possible.
Certainly possible, I agree. But his argument against formalism was often that it emphasized too much language. So it's a question of emphasis, right? He's like, yeah, it's mostly the mental stuff, and you use communication to do mental stuff. Whereas the formalists were like, nah, I don't need to incur like intuitions in you. I can just show you the proof. So it's still a difference, but I agree it's not as black and white as this might indicate.
There's one anecdote. I think it's actually true, but I think there's a picture in the Bernays book that the belief of Hilbert in the solvability of any mathematical problem was so strong that the inscription on his tombstone is, I think it's in German, wir müssen wissen, wir werden wissen. So we have to know. We
will know. Yeah. And he repeats both the no ignoramus claim that there's no unsolvable question and this in 1930. And he podium bounding excitement.
Yeah, right.
We must know, we will know.
The radio address was recorded, and you can listen to it now. It's really fun.
I didn't know that.
Yeah, I'll send you the link.
Yeah, that's great.
Here he'll say, "Wir müssen wissen, wir werden wissen." Okay, we'll stop it for that.